Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about telescopes and very specifically optical telescopes using visible light. So this is likely what you think of when we talk about telescopes. However, we will see in future lectures that there are other types as well. So what is an optical telescope? Well, let's go back even earlier. What is a telescope? And it is just a device that is used to observe astronomical objects. It gathers light, which remember that can be any type of electromagnetic radiation, and brings that light to a focus. It allows us to see fainter objects than would otherwise be visible. So we see a telescope here, actually multiple telescopes, one main lens and other smaller scopes attached to it, all pointing in the same direction in the sky. Now let's look at the early telescopes. The telescope was actually invented in 1608. And as we mentioned in a previous lecture, it was not invented by Galileo. Galileo did hear of the invention and made his own telescope. And he was the first to observe the sky and to record his observations, which is often why he gets credit for the telescope, but really did not make the invention himself. It is something that he heard of. Now, what types of telescopes are there? Well, when we're talking about optical telescopes, there are two types. You can have a refracting telescope, which uses lenses, or a reflecting telescope, which uses mirrors. So here we see a refracting telescope. It has a primary lens up at the top here, and then an eyepiece, another lens down at the bottom. Now you can also have a reflecting telescope, which has a large mirror down here that collects the light and reflects it back up. Now, since it's reflecting it back up out into space, you need a secondary mirror then to divert that light to an eyepiece to be able to see it. Now, there are several different ways that you can do this, and we'll take a look at them here. And here are three different types that are used. There is the prime focus where you need nothing else. That brings it to a focus right up here. And you can put your detector right inside the telescope. Now this works as long as you have a big enough telescope. If you're looking at a small telescope, trying to put any detector there could block a big part of the light coming in and would make it rather inefficient. However, if you have telescopes that are many meters across, a small detector up here is not going to take up a significant amount of space. Now we also have a Cassegrain focus shown here. The Cassegrain focus, the light bounces off the mirror, back up to the secondary mirror here, and then back down through a hole in the primary mirror, and then brought to a focus down past this. So that is one way. This is convenient because you can put instruments at the bottom of the mirror, and that put makes them very easy to be stable, so that you're putting them where all the weight of the telescope is, making it easier to keep the whole system stable. Now another one that is often used is the Newtonian focus. Again, it bounces off the mirror here up to a secondary mirror, which is angled and sends it off at an angle to be seen. Now that can be convenient for some telescopes, especially smaller telescopes, to be able to put the eyepiece at a convenient location. However, it can be inconvenient if you're trying to put a heavy instrument there, because you're applying a lot of extra torque to the system, which will put extra force on that. So it really depends on the details of exactly what you want to observe with these different types of telescopes. Now, when we think about telescopes, we think about what their powers are, what they can do. Well, there are three different powers a telescope has. It has light gathering power, resolving power, and magnifying power. For light gathering power, it depends on the square of the size of the primary lens or mirror. So in order to have more light gathering power, you want a larger telescope that will give you more light gathering power. It'll allow you to see fainter objects. The resolving power also depends on the size, but not on the square of the size, just on the size of the primary lens or mirror. And a larger lens or mirror will have a smaller resolution, which is good. You want small resolution because that is better resolving power. That it means you can see more closely separated objects. And finally, we have magnifying power. This does not depend on the sizes of the mirrors, but depends on their focal lengths. So it depends on the focal length of the primary mirror or lens, which is generally fixed, and the focal length of the eyepiece. This is the least important of the three powers. So you may hear about the magnification of a telescope if you're buying one someplace. But if it's emphasizing the magnification, that's usually the least important thing. What you need is quality optics and the larger mirror to be able to see fainter objects. So a larger mirrors or lens is going to do a lot better. And you have to remember that you can also adjust the eyepiece to be able to magnify things as well. So if you're not getting as much light, you can't magnify very little light. It will spread it out too much and you will have no image. If you don't have a lot of resolution, you can magnify that, but it's not going to give you any better resolving power. You can't make it better by magnification. It will only enlarge the blurry image. Now let's look at some of the limitations of a telescope, and a couple things that we have here. One for lenses is chromatic aberration. This is very common, especially in inexpensive refracting telescopes, because the lens acts like a prism and it splits the light into its component colors. So the blue light comes to a focus here, the red light to a focus here. Where are you trying to observe? If you focus the blue light, then your red is out of focus. If you focus the red light, then the blue is out of focus. So you may see this with an inexpensive refracting telescope, that if you look at a bright star, you might see a nice star image with a blue or a red halo around it. And that just depends on where you're bringing it to a focus. This can be adjusted by adding multiple lenses and trying to adjust some of it, but it's never completely eliminated. And of course, the more lenses you add, the more absorption of light you have going through these. There also are some limitations on the size. How big can you make a lens or a mirror? Well, a lens you have to hold by the edges. You cannot support it from behind because that would block the light from coming through. So I can't put a big support right behind it here and here. That would block light from coming through this lens and would make it impossible to be able to observe with it. So a larger mirror, it's a lot easier to build a larger mirror than it is a large lens, which is why the largest refracting telescope is about a 40-inch mirror, sorry, 40-inch lens, which was completed in the late 1800s. Nothing has been larger than that since. Now we certainly could build a larger one today, but not coming close to the large mirrors that we'll be talking about soon. Now, one of the other limitations that applies to all telescopes is what we call seeing. Seeing is the blurring effect of Earth's atmosphere. So the light comes in all nice and smooth from space. It goes through this turbulent atmosphere and then the light is all distorted. And that makes it very hard to see a clear image. And the resolution is really not defined by the telescope, at least for a telescope on Earth, but is often defined by the atmosphere. So you want to put a telescope in places where the atmospheric effects are the least. That's why a lot of telescopes are in high mountains. Now another way to get around this is to adjust the optics. And that's what we call active or adaptive optics, which means instead of building a big thick mirror to keep it from moving, you build thinner or segmented mirrors that are computer controlled, and you can deform them to account the shape to account for atmospheric turbulence. How do you measure that? Well, the image is shown here. So here is shooting a laser, not to the center of the galaxy as is shown here. The galaxy is there, but is actually shooting it up into the upper atmosphere and exciting the atoms up there, which can then be observed. Now, since we're making in a way an artificial star, we know its properties, and we can then say when the light comes back, we know what it should look like, and we know what it does look like. We can tell what the atmosphere has done, and then we can apply that correction to fix this artificial star, but we can also use it to fix regular observations. So it's a way to take into account and remove the effects of the atmosphere. Of course, another thing to do would be to get it up above the atmosphere, and we'll look at space telescopes in another lecture. So let's look at a few of these telescopes. This is the largest refracting telescope. You can get an idea of how large it is. You have the large lens up at the top, and then all the way down to the eyepiece down at the bottom. So it takes a lot of material there to be able to balance this very massive tube. Remember, the light has to go all the way through that tube. This was completed in 1897 and was a 40-inch lens. And as I mentioned previously, that is the largest one to date. Another large telescope is the Hale telescope on Mount Palomar, completed in 1948, and for about 3 decades was the largest telescope in existence. It has a 200-inch mirror, which is about 5 meters. And while we'll see it's dwarfed now, it is still a very large telescope, very large mirror down at the bottom. And the apparatus to hold it, you'll notice that it's all open. There's no reason to have all of that solid metal. If it's enclosed within a dome, you don't need that, and you can get rid of that extra weight. But you can see the massive size of the telescope by all of the mechanism that is needed to be able to steer this telescope and keep it pointing at the right position in the sky. Now let's look at a few newer ones, and here is one example. This is the Very Large Telescope, sometimes called VLT. And this was completed in 2000 and has 4 telescopes. You can see the 4 domes here, which can be used together if needed. And they are 8-meter mirrors. So compared to the 5-meter mirror that we just looked at for the 200-inch telescope, these are significantly larger. And remember, the larger the telescope, the fainter the objects we can see. And with things like adaptive optics, we can actually get very good resolution out of them as well. Now we also have the Large Binocular Telescope. You might figure out why it gets its name. It's 2 telescopes together, looking like a pair of binoculars looking out to space. This is again similar size to 8.4-meter mirrors. But since they're used together, it has the effective size of an 11.9, almost a 12-meter mirror. And this was completed in 2004. And then we have the Gran Telescopio Canarias, and that was completed in 2007, which is a single mirror that is 10.4 meters. Now you think about how big these telescopes are getting. It's very hard to build one mirror this size. So this is actually in hexagonal segments, 36 of them, that are then put together to be able to use it as a single mirror. Now note again the structure. It's very little. It's just enough structure to hold, in this case, the secondary mirrors in place. You don't need a lot of that structure and can save a lot of weight by not having a completely enclosed tube. Now for smaller telescopes that you're using out, say in a parking lot, you may need that to shield from light. But something here in the that is out in an enclosed dome, you really don't need all of that extra weight. Now let's look a little bit about the future as to what's coming. Well, one that is being worked on is the European Extremely Large Telescope, which is projected now to be completed in 2027. So this is the conception drawing of this large telescope. It is a 39.3-meter mirror. And it is, so that'll be much larger than any of the other ones that we've talked about. Progress is going on this, and here is the image as the setup as of 2022 as to the beginnings of setting this up, and eventually will be the largest telescope and will be a big increase in our understanding by being able to see far fainter objects. Now we've looked at some of the telescopes, but where do we want to put these telescopes? Well, there's a couple things to think about. Weather. Now, old telescopes were put where the astronomers were. So Harvard would have theirs near Boston and others would be outside of Chicago or Los Angeles. However, this is not necessarily the best places for clear weather all the time. And the bright city lights are also not very good for these. So you want to look for places where there's clear weather. You want to avoid water vapor. Water vapor absorbs some of the infrared light. So the higher you can get up, you're going to get better weather and you're going to be able to observe some infrared. You need dark skies. This is a map of the world showing light pollution and how bright areas are. So areas that look completely black are the very darkest. Some areas are extremely bright. And you notice that especially the eastern part of the United States. You'll notice much of Europe there, even parts of China, Korea, Japan, very bright, India, and some other areas, a lot of areas even in the Middle East, very, very bright, and then makes it difficult for telescopes. Now, of course, you have to look at these other areas as to whether they're going to have good weather too. So a lot of places end up being the very desert areas where you're going to be able to get the best weather and you're going to be in mountains. So mountainous desert areas are among the best for getting this. And you also get good seeing by getting up high in the atmosphere. The less atmosphere, the better. So let's go ahead and finish up as we do with our summary. And what we've looked at today is that what is a telescope? Well, it's used to gather light from distant objects and bring that light to a focus. We looked at the three powers of a telescope: light gathering power, resolving power, and magnifying power. And we looked at modern telescopes and how they are much thinner and larger than the previous telescopes of even just a few decades ago. So that concludes this lecture on optical telescopes. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.